Okay, so this class we're going to learn rate law and reaction mechanisms. What they mean will become clear once we actually learn them. So first of all, rate law. We learned that concentration affects reaction rate. More specifically, higher concentration results in higher reaction rate. Right, but we don't really know how much does it affect the reaction rate. If I double concentration, do I double the reaction rate or what? So that's basically what we're going to learn in this class. So consider the equations on the screen. A plus B, you get products. Big A, big B are the reactants. Lowercase a and lowercase b represent the number coefficients that we use to balance the equations. Now, the rate of reaction, how fast the reaction actually progresses, it is proportional to the concentration of the reactants A and B. They have to be raised to a power of the positive integer or zero. It is not simply directly proportional to just A and B. All right, so it is A to the power of something and B to the power of something. So we use m and n's to denote those integers. So the rate of reaction for this specific equation will be rate proportional to the concentration of A raised to the power of m times the concentration of B raised to the power of n. That little symbol that looks like a fish, it means proportional. M and N are positive integers or zeros. So it could be 0, 1, 2, 3, blah, blah, blah. All right, so you can see that the rate law depends on the concentration of the reactants. But it could be the power of a reactant. We just don't know that. So let's rewrite this so that it becomes a mathematical equation that we can calculate with. So rate equals to a constant, K, because proportional, by how much, let's just call it K, times A to the power M, B to the power of N. K is the rate constant. And this constant is determined empirically in the lab, or there's no way to predict this. And this is only valid for a specific reaction at a specific temperature. If you change the reaction or if you change the temperature, you get a new value of K. So K is very specific. This thing right there, this entire thing is the rate law equation. The rate law equation tells you the relationship between the concentration of the reactants and the rate of reaction. Okay? How do we know what the rate law and the rate law constant is? Well, you have to use experiments to figure that out. You cannot just look at the equation, the balanced chemical equation, and figure that out. None of these numbers in the rate law relates to the balanced equation at all. So M and N are not the same as the coefficient in the balanced equation. You must do an experiment and then use the data to determine what the rate law is. All right, so the exponent of the rate law, we call them order of reaction. An order of the reaction is simply the exponent used to describe the relationship between concentration and rate. So let's look at this example. You have 2A plus 2B plus 2C, you get a product. And it just so happens that the rate law for this reaction is K, A to the power 1, B squared, and C to the power of 0. Again, I reiterate, the exponents in the rate law, they have nothing to do with the balanced equation. In the balanced equation, you have a 2, 2, and 2. Well, they're not 2, 2, 2. It's 1, 2, and 0. How do we know it's 1, 2, 0? Well, we do an experiment. So I made this one up. Okay, I can make it up to be anything I want. It doesn't have to match. What that means is the reaction is first order with respect to A because the exponent is 1. This is second order with respect to B because it's B squared. And this is 0 order with respect to C, because C is raised to the power of 0. And you know, mathematically, if you raise something to the power of 0, you get 1. So this is saying that C does not affect the rate of reaction. You can also add up the orders to get the overall total order of the reaction. So that is the sum of all the exponents. So in this case, 1 plus 2 plus 0, the total order is 3. All right, so does that make sense so far? All right, so let us look at example 1 then. For the reaction, 3x plus y, you get z. We collected some data. Somebody ran this experiment 8 times, and he changed the concentration of one of the reactants every time and measured the rate of reaction. So our job is to determine the order of the reaction with respect to x and y, write the rate law equation, and determine the value of k. So how do we go about doing this? Well, we have to look at the table first. This person did 8 trials, so 8 different experiments. If you look at the first row, the concentration of x and y are both 0.1 moles per liter, and the rate is measured to be 10 moles per liter per second. All right? Now, if you look at experiment 2, all that's different is that the concentration of x is doubled. It went from 0.1 to 0.2. The concentration of y stayed the same. So what happened to the rate? Oh, look, the rate doubled. It went from 10 to 20. Okay, so what does this tell you? This tells you that if you double the concentration of x while keeping y the same, you double the rate of reaction. All right, double x, you double the rate. Experiment 3, you tripled x. You went from 0.1 to 0.3. Y didn't change. The rate went from 10 to 30. So you triple the concentration of x. That means you would triple your reaction rate. Same thing with experiment 4. You quadruple the concentration of x. You quadruple the rate. Okay. Now the same experiment was done with y. So this person kept all of the x to be 0.1 this time, but changed the y into 0.1, 0.2, 0.3, and 0.4 and looked at what happened to the rate. So in row number 5, you have 0.1, 0.1, 10. Well, that is the same as 1. But now if you double y, you give it 0.2 in reaction 6, the rate quadrupled. Right? You double y, the rate is quadrupled, times 4. You triple y, the rate is multiplied by 9. So using this information, we can determine the order of reaction. So from the first 4 experiments, we can see that if you double x, you double the rate. So they're changed by the same factor. So rate is directly proportional to x to the power of 1. Double x, double rate. Triple x, triple rate. Okay, you times x by 10, the rate times by 10. That means this is first order with respect to x, because it's literally the same number. If you look at the information from 5 to 8, you can see that if you double the y, the rate quadruples, so it's 2 to the power of 2. That means you need to raise y to the power of 2 in order to get the effect you see on the rate of reaction. So that means the rate is proportional to y squared. Right? If you tripled y, then 3 squared is 9. Rate is multiplied by 9, which is what we see. So this is a second order reaction with respect to y. Does that make sense? So therefore, if you want to write the rate law, you'll have rate equals the constant k times concentration of x to the power of 1 times the concentration of y squared. That's your rate law. Do we have any questions regarding the rate law and how to determine the rate law from a data table?
Wait, so when would it be 0?
When would it be 0? When you have no effect.
Okay.
Yeah, in this question, there is no zero, but if you double something and change nothing else and the rate stayed the same, well, you had no effect. That would be a zero order. We need to calculate K. That's part of the question as well. All right, but how would you calculate K? Well, you can just substitute any row into the equation. Okay, experiment 1 to 8, they're equally valid. I'm just going to choose 1 because it has the simplest numbers. Doesn't matter which one you choose, really. So R is equal to 10. X is 0.1. Y is 0.1. So I just have to substitute this into the equation, and I can just solve for K, right? Just rearrange everything, isolate K, and voila. K is 1.0 times 10 to the power of 4, and the unit is liters squared per mole squared per second. Does the unit really matter? The answer is no. Okay, if you just look at that unit, that looks ridiculous. The unit doesn't matter because, again, K could be basically anything. It just so happens by accident that this question had x to the power of 1, y squared. And because you had to square y, you have to square the moles per liter. You got this unit. What if x was also a second order? So x squared, y squared. Then you wouldn't have this unit anymore because you would have squared the moles per liter on the x as well. So this is just an accident. It just so happens that for this question, this is the unit. The unit could be anything. Right? It is subject to change, so it doesn't matter. It doesn't tell us any stories. We don't have to worry about the unit for K. We just care about the value. Does that make sense? So that's K, and that's how you would solve that question. So here's example 2. Same idea. Here's the data table. The reaction is A plus B, you get C. Determine the rate law equation and the value of K. So I'll give you a few minutes to practice, and then I'll take this up. Use the same strategy I used for example 1. All right, so for example 2, you have a table, yet again, and you're asked to solve for the rate law and K. The first thing you do is you look at the table, you compare each experiment with each other. So in row number 1, experiment 1, A has a concentration of 2, B has a concentration of 1, and the rate is 0.5, okay? Compare experiment 1 with 2. What's the difference? Well, you doubled A because it went from 2 to 4, and the rate doubled. You didn't change B at all. So that means A is directly proportional to the rate. So the order is first order. And if you look at 2 and 3, you made A stay the same, so 4 and 4. B, you doubled. The rate actually increased by a factor of 8. That means you multiply by 2 to the power of 3 to get 8. You doubled B, which multiply by 2 there, but you multiply by 8, so that's 2 to the power of 3. So this is cubic. Rate for B is the third order. You see what I mean? So you see how you could determine that? Well, once you know these, you can just write the rate law. So rate law is K, A, B to the power of 3. And of course, you can solve for K. You can just randomly choose one. I think I just chose the first row for simplicity. Isolate for K. You can cancel the units, and you would get K equals to 0.25. The unit is, in this case, liters cubed over moles cubed per second. This is a different unit from the previous K. So as you can see that this really doesn't matter. The thing that matters is the 0.25. So to finally finish the question, the rate law is 0.25 A times B cubed. All right, do we have any questions regarding rate law? No, good. Okay, so you should get the same answer here. Example 3 is long, but it's not difficult. Right? It's just a lot of reading to do. An investigation indicates that the initial rate of the reaction represented by that beautiful equation right there at 25 degrees is 3.2 times 10 to the negative 3 moles per liter per second. When the initial concentration of bromate is 0.1, Initial concentration of bromide is 0.1, and the initial concentration of hydrogen is 0.2. Okay, that's a long sentence. All right, let's break that down. Let's try to understand that. So basically, this is saying the rate is 3.2 times 10 to the negative 3. That's the rate of reaction. The concentrations of the three reactants are 0.1, 0.1, and 0.2 respectively. Okay, so basically it just gave you all the values. So what do you need to do? Well, the reaction is first order with respect to bromate, BrO3, and also the first order with respect to bromide, Br, and finally it is second order with respect to hydrogen. So the order is 1, 1, 2. So you have all this information. You have to determine the initial rate if the hydrogen ions are doubled, but you don't change anything else. Right, so double hydrogen, what happens to the rate? And B, find the rate constant K. Okay, so again, I'll give you around 2 minutes. It's a long question, but it's actually very simple. It gave you basically all of the numbers. So try to work this out, and then I'll take that up. All right, so to solve this problem, you just basically need to write down all of the numbers, and the answer should be very clear. So the first question asks you, what happens if you double hydrogen? Well, first of all, this is the rate law. How do I know that? Well, it said it was first order with bromate, first order with bromide, and second order with hydrogen, so this must be it. I raised hydrogen to the power 2 because it's second order. Now, if you double hydrogen, if you instead of H, you have 2H, then you will square the 2 because the whole thing is squared. You would quadruple the rate because the second order. So that means if you double hydrogen, the rate initially is given to be 3.2 times 10 to the negative 3. Well, you have to times 4. And that's a very simple calculation. Multiply by 4. You have 1.3 times 10 to the negative 2 moles per liter per second. All right, so part A is very simple. If you double hydrogen, the rate is quadrupled, and the specific number is 1.3 times 10 to the negative 2. Now, to find K, again, here is the rate law. All you have to do is just sub in all of the numbers the question gives you. Just be careful, don't copy them wrong. First of all, I'll rearrange to isolate for K. You put the numbers in. R is 3.2 times 10 to the negative 3. BrO3 is 0.1. Br is 0.1. Hydrogen is 0.2, but you have to square the hydrogen. So you put all of this in your calculator, and that should come out to be 8. Okay, again, the unit doesn't really matter. It's liters cubed over moles cubed per second. K is 8. Okay, and you do sig figs, 2 sig figs, and that's it, you're done. Right, so any questions regarding rate law? This is it. That's all we're going to spend on rate law. All right, cool. So the next part of the lesson is our last little bit in Unit 3. Before I tell you what that is, let me tell you a story first. This relates to what we're going to learn. Now, on April 29th in 2015, I was in the city of Wuhan. Why was I there? Well, because I was teaching there at an international school. But on May 1st is a holiday in China. So I get a week off. So I'm like, I'm going to go back to Toronto for that week because, I want to be in Toronto. So I buy some plane tickets online. I fly to Toronto. And I land in Toronto on April 30th, 2015. Okay, you feel me? And then after having spent a week in Toronto, I'm like, okay, it's time to go back to work. So I hop on the plane on May 7th, 2015. And then I land on May 8th, 2015, back in Wuhan. And then I went back to work basically a few hours later on Monday. Now, why am I telling you about my life? You probably don't care. Well, what's interesting is I can write down my flight itinerary like a chemical equation. Right? So I start from Wuhan, I go to Toronto. And then I go from Toronto back to Wuhan. Okay, cool, but who cares, right? Well, there are no direct flights between Toronto and Wuhan. So this isn't the whole story. I did go from Wuhan to Toronto, but all I told you was where I started and where I ended up. I didn't tell you how I got there. So because there are no direct flights, I must have transferred somewhere. You see what I mean? So here is a more detailed look at my trip on those days. I started in Wuhan. I ended up in Guangzhou. I had to transfer there. That's a larger airport. It has an international airport that reaches the North America, I suppose. All right, and then I hop on a flight and I land in Chicago. After having spent a few hours in Chicago, I hop on another flight. I finally end up in Toronto. Okay, that was really exhausting. So I had to do 2 transfers. Oh, cool. So I spent the week in Toronto. That was fun time. And then I have to go back to Wuhan to teach. So I hop on the plane. Wait, before I do that, well, here is the itinerary. So first I started from Wuhan. I went to Guangzhou. That's the first equation. From Guangzhou, I went to Chicago. That's the second equation. And then finally from Chicago to Toronto. Just like in a chemical reaction, you can cancel stuff, right? I can just cross out Guangzhou because it happens on both sides. And then I can cancel Chicago because it happens on both sides. So really, you end up with the next equation that tells me I went from Wuhan to Toronto. Those are just the intermediate steps. Okay, you see what I'm getting at? So to go back to work, I have to go back to Wuhan. So I didn't take the same trip. I flew to Dallas, one of the worst airports I've been to. Like, my goodness, I just wanted to transfer there. I stood in line for 2 hours to get into customs. It wasn't even a long line. It's just they take so long per person. It was the first airport where they asked me to remove my shoes and my belts. I had a bad experience in Chicago as well. I told myself I would never transfer in the United States again. It just takes so long. Anyway, finally, after that long wait, I get on the plane. I fly to Shanghai. Again, a terrible experience in Shanghai. There was a storm and the planes couldn't take off. I had to spend like 3 hours on the plane just in the airport and then tell, hey, get off because, we can't fly today. Get a hotel. I have to book my own hotel, pay for that hotel, and I get to miss a day of work. And I don't get paid for that day. So, terrible, terrible experience. Anyway, and then I get on the plane and I end up in Wuhan again. Okay, so that is my trip back to Wuhan. So if you write this out, I started at Toronto, I went to Dallas, and then I started at Dallas, I went to Shanghai. From Shanghai, I went to Wuhan. So I can cross out Dallas because it appears on both sides of the equation. I could cross out Shanghai because, again, on both sides of the equation. So the next equation will be from Toronto to Wuhan. You see what I'm getting at? You probably don't care where I've been. You just wanted to know I started in Toronto and landed in Wuhan. Actually, you probably don't want to know that. That's just an example. In chemistry, we have much the same thing. In a reaction, you have the reactants and the products. It doesn't really tell you how you got there. It just says you started with the reactions and you ended up with these products. Just take my word for it. So the balanced equation only tells you the destination. It doesn't tell you the path it took. It doesn't tell you how many steps did it take, and what did you make in the middle? Nobody knows. So a reaction mechanism tells you that information. It gives you a series of elementary steps, one step at a time. How did you arrive at your final product? And these are determined experimentally. What is an elementary step? It is one of the simplest steps that you can have. You cannot explain that with a simpler step. So for example, this collided with this. That's it. Like, you can't break it down more than that. And then this big thing collided with some third particle, and then finally this broke off, and then you have your final product, for example. Right, so those are elementary steps. For example, step 1, A plus B, you get C plus D. Okay? Step 2, you take the D that you made, you combine that with E to make F. So your final overall reaction is AB plus E, you get C plus F. D is gone. You have consumed D. You made D in your first step, but then you immediately used it again. So that does not appear in your final equation. You cancel it out. Does that make sense? So these are reaction mechanisms. It tells you how you got to the final step. So kind of like what we did with Hess's law. So consider this real chemical equation. You have NO2 plus CO. You get NO plus CO2. Here is the rate law. We determined the rate law experimentally. We did some experiments and we figured out, okay, so that's what affects the rate of reaction here. Rate equals to K NO2 squared. This has nothing to do with the balanced equation at all. Okay, just to remind you. All right, so we have determined the mechanism of the reaction as well. So to get this net reaction, it takes 2 steps. Or 2 elementary reactions. Step 1, you take NO2, you combine it with another NO2 to make NO3 and NO. That's step 1. All right. Step 2, you take your NO3, you combine that with carbon monoxide to make NO2 and CO2. That is step 2. You see what I mean? So it takes 2 steps to get to your final product. But if you look carefully on the right, it says slow step and fast step. So they occur at different rates. Some steps are slower than others. All right? And step 1 happens to be the slow step. And the slow step is called the rate determining step, which means it determines the rate of the reaction. Your reaction can go only as fast as the slower step. Increasing the fast step doesn't actually increase the rate of reaction. If you want to ask why, a simple analogy will quickly show you why. Imagine that you want to deliver a parcel to London, UK. You have to cross the Atlantic to get to the UK. Okay, so you go to Canada Post, you drop it off, you write down the address, and hopefully the person in the UK can get it soon. You know what? You really want the person in the UK to get it. So you call up the Flash from DC Comics, the fastest man alive. He can run, well, in the comics, they say he can run faster than the speed of light, but we know that's impossible. So let's just say he runs at 99% the speed of light, okay? So Flash picks up your package, runs to St. John's in Newfoundland and Labrador, drops the package off at the harbor. Now, he can't swim, so that's as far as he can go. And that trip took him less than 1 second because he's the Flash. And then at the harbor, a turtle grabs the package, put it on his back, and swims across the Atlantic to London. Okay, when do you think the guy in London will get the package? Anytime soon? No, probably not. Like 10 years later, there's my package because the turtle took that long to swim across the Atlantic. Yeah, I'm surprised the turtle made it at all. So which was the rate determining step? Of course, it's the turtle. You see what I mean? You'd be like, you know what? I really need that guy to get the package soon, man. Come on. You talk to the Flash. Can you run faster? Because I need the guy to get the package sooner. You can't take 10 years. Flash said, no problem. Let me run faster. Okay. Instead of 99% of the speed of light, let me run at 99.99999% of the speed of light. So boom, there, I'm at the harbor. Here, turtle, come on, hurry up, take the package. And the turtle swims. 10 years later, the guy gets the package. Made no difference. Okay? You can't tell the Flash to go faster and expect the package to be delivered. Because the turtle is the rate determining step. You gotta wait for the turtle. It doesn't matter how fast the Flash goes, the turtle is the bulk of the trip. So that's why the slow step determines the rate of reaction, not the fast step. Does that make sense? All right, so if you look closely at the 2 equations, you can see that NO3 cancels out with NO3. You see what I mean? If you cancel out, you were created at first, but then you were immediately consumed, then you are something called a reaction intermediate. You were made as an intermediate, and then you were used to build something else, and you disappeared. Right, so NO3 is the reaction intermediate because it appeared in the product in the first step, but it was used as reactant in the second step, and it's gone. That does not exist in your final net equation. Remember how I said that the rate law equations, R equals to K, blah, 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 that cannot be derived from balanced chemical equation. It has nothing to do with the balanced equation. But it can be derived from the elementary steps, specifically the rate determining step. All right? The rate law is derived from the rate determining step in your elementary step. There is a pattern. In fact, it is literally the coefficients of the balanced equation in the slow rate determining step. Not the final equation, but the slow step. This really shows you that. Okay, so here you have the two steps. The top equation, step 1, is slow. That's the rate determining step. You can cancel the NO3s. That's the reaction intermediate. You can cancel the NO2s. All right, because they happen on both sides, and you write your net equation. Oh, that's exactly what you have. Right, this is your final product. So, since CO, the carbon monoxide, it is a reactant, but it only appears in the fast step, and it does not appear in the rate determining step. It has no effect on the rate of the reaction. Increasing the concentration of CO doesn't actually speed up the reaction. Just like telling the flask to run faster is not going to help because the turtle still swims very slowly. So that is not in the rate law. Well, who is in the rate law? Right? Who is in the rate law? NO is in the rate law. NO appears twice. You see what I mean? In the rate determining step. The slow step, step 1, is NO2 plus NO2. It happens twice. So that means it has double the effect on the rate of reaction. So thus, the rate of the reaction is the second order to NO2, but 0 order to carbon monoxide. So that's how you get the rate law, from the rate determining step. Do we have any questions about that? That's the rate law. NO2 squared. Where did the 2 come from? The square comes from the fact that there are 2 NO2s in the slow step. This table summarizes that. This is the rate determining step, okay? If you have an elementary step that literally says A becomes the product and that's your slow step, well, the rate law will be just Ka. If your elementary step for the slow step is A plus A, you repeat the A twice, the rate law will be A squared. And if your rate determining step is A plus B equals product, then your rate law will be just AB. And you don't raise them to any power because they only appear once. Okay, I hope I made that clear. The rate law depends on the coefficient of the rate determining step, not the overall balanced equation. So let's look at example 4. Nitrofluoride gas, NO2F, is a strong oxidizer that is sometimes used as rocket propellant. Complete useless sentence. Nitrofluoride gas can be synthesized from gaseous nitrogen dioxide and fluorine. The balanced equation for this reaction is, there you go, that one. 2NO2 plus F2 is 2NO2F. And somebody determined the rate law in a very dangerous experiment because there's NO2 and F2, both of which will kill you, but he did it, or she. Rate is KNO2F2, all right? They're both first order. So somebody suggested a mechanism for this reaction. Now, suggested, because we don't know what the mechanism is, but here's an idea. I'm just going to pitch it out there, right? I think the mechanisms are as follows. NO2 plus F2, you get NO2F first, plus a fluorine radical F. No 2, just F. That's the slow step. And then you have the NO2 plus the F radical, just the lonely F, and then you have NO2F. That's the fast step. This could be the mechanism here. So let's decide, is this a plausible mechanism for this reaction? And notice the word plausible. Plausible doesn't mean this is the answer. It means it's believable. Right? And also plausible is not the same as possible. Right? Let's say Calvin's late for class. Now, Calvin, why are you late for class? If you tell me you missed the bus, that's not plausible because you don't take the bus to class. You see what I mean? If you tell me you had to kill the Joker on your way to class, I don't believe you. That is not plausible. But if you say you overslept, that is plausible because that does happen. See what I mean? But it doesn't mean you're telling the truth. Maybe you slipped on the stairs. I don't know. But plausible means it's believable. It is possible, but we just don't know whether it's true. So is this plausible? What do you need to determine to figure out whether this is plausible? So first of all, do you think this is plausible? Anyone?
No.
No, why not? What's wrong with it?
With the F2 and the slow step, that would be the, what's it called? I forgot what it's called.
The F2, the reaction intermediate?
Yeah, wasn't it?
The F2, like fluorine gas? That's just straight up a reactant because it appears in the final equation as well. So first of all, what do you have to satisfy in order for this to be true in the first place? But you can't just randomly come up with a few steps and call it a mechanism. You have to satisfy certain conditions. You see? Two conditions must be satisfied. In order for this to be true, well, the elementary steps that you propose, they must add up to the net equation. Right? If they don't even add up to the net equation, that is the wrong steps. Right? Just like in Hess's law, you have to add them up to the net equation. Well, same here. They have to add up. Number two, you must check the rate law. It has to match the rate law with the rate determining step. Whatever the exponent on the rate law is, it must be the same as the coefficients in the rate determining step. If you can satisfy both conditions, you are a candidate to be a real mechanism. Right, that's all I can say. I can't say for sure that you are correct, but no, it is certainly possible. You're in the running. So let's check. Those are the two steps that we propose. Well, step one, if you add them up, what do you get? Well, you cross out the two F's because they appear on both sides. And, well, that's it. That's all you can do. So you add them up. You have 2NO2 plus F2. You get 2NO2F. That's your net equation. Oh, look, this is exactly the same as the net equation that we know. So you put a check mark. Okay, you passed step one. So they do add up to the net equation. Let's check out the second condition, the rate determining step. The rate determining step has NO2 and F2 as the reactants, and the coefficients for both are 1. So the rate law should therefore be K NO2 F2, both raised to the power 1. Is this the same as the rate law that we determined empirically? Well, yes, it is. It's exactly the same thing. All right, so you passed both tests. They add up to the net equation, and your rate determining step corresponds to the rate law. So basically, you pass all the tests. It is plausible. So there's no reason to say you're wrong, but we can't tell that if you're right. We're just going to say it's plausible. Let's investigate more. You see what I mean? In order to be plausible, you must satisfy both conditions. If you fail at least one, you cannot be correct. There's no way you are the correct mechanism because you have to satisfy both. Right. Is that clear, everyone? All right, so before I end the class, I just want to mention one more thing. I neglected to put this in the PowerPoint, but it is kind of important. You need to know how to identify reaction intermediates. Right? Like on this slide right now, you can see that I crossed out the F, right? That is the reaction intermediate. The F is made in the first step, but it is immediately consumed in a following step. So that it's canceled, doesn't appear in the final equation. That's a reaction intermediate. That was in the lesson. But what I forget to put in is catalyst. I could ask you, is there a catalyst in this reaction? Right, so how would you tell if something is a catalyst? Well, a catalyst will be in the reactants first. It will bond with something to make something different. And finally, in the final step, you have to spit it back out. You have to reform the catalyst because you cannot consume a catalyst. So let me give you an example. I'll write this on top. Let's say you have A plus B. You get C plus D. Okay? And then you take D plus E. You get B plus F. So let me ask you, what is the reaction intermediate? What letter? Everybody should be able to tell me which one is it. Guys, something that's made in the first step, used in the second step. Come on, folks. There's only one thing that matches that description.
Right?
I can't actually hear you.
Oh, D.
D. Oh, yes. D is in fact correct. All right. D is synthesized in step 1, but that doesn't appear in the final product because it's been consumed in step 2. So D is the reaction intermediate. All right, intermediate. Okay. What is the catalyst? Remember, a catalyst is used as part of the reaction, but it is reformed at the end so that it is not consumed.
Is it B?
It must be B, okay, because B is used to bond with A to make C and D. All right, and finally, at the final step, B is synthesized again. So that way you can cross out B. It does not appear in your net equation. Catalysts should not appear in your net equation because they're unchanged. So that would be the catalyst. Okay, so make sure you can tell the difference between the intermediate and the catalyst in reaction mechanisms. I once tested this on a test, and I gave the students a couple of lines of mechanisms, and I asked, well, it's really poorly phrased now that I look back at it. So here's what I wrote. Determine whether this reaction has a catalyst, and if so, identify the catalyst. So that's the question. Very ironically, the catalyst in the reaction is nitrogen monoxide, NO. Right, so here's the problem. So the student, I marked the test, and one of the students just wrote NO, both capital letters. I'm like, are you saying no, there is no catalyst, or are you saying nitrogen monoxide is the catalyst? So I gave them the marks for the benefit of the doubt. I just, that looks like nitrogen monoxide. So yeah, that's a terrible question on my part, but you do need to know how to find the catalyst in a series of reaction mechanisms as well as the intermediate. Right, so do we have any questions regarding reaction mechanisms, rate determining step? All right, so that will conclude the lesson for today. So we learn about rate law, the order of reactions, and how this is not related to the balanced equation. All right, and also we learn about elementary steps and how they add up to the overall step, and that will be a reaction mechanism. in the elementary steps, one of them will be the slowest step. That will be the rate determining step. The rate law is derived from the rate determining step. Okay, so any questions before we end it? All right, sweet.